Hello. Pointer. Okay, I tried to cover something quite simple now compared to other presentations. So it is one of the projects I have been working on for last 3 years, and now I try to cover like different aspects what we have learned from this one. So essentially the problem what we were facing with the SUTD pavilion was how to fabricate something in a medium size but with a low cost, and we thought it would be nice to do out of flat material. And this flat material kind of restricted us what we can do, but we also saw it as an opportunity to look into can we do out of flat material three-dimensional curvature in shape. So that I started a software application to apply it on a different occasions. And what I found, it's very important to keep the input super flexible, so you can move one software from one project to another one. And another thing is to allow users to describe what the end result should be, rather than describing every single decision. The third one is if it becomes semi-architectural scale, there's all sorts of structural problems. And usually the problem is not that nobody can calculate them, but it's rather a legal problem, is it allowed to calculate in one way or another way? And if the local government is actually accepting these kind of calculations, so it's if you are not calculating by code, then you need to do a test, and the tests are making things more expensive. And the third one is the assembly issue. If we do a project which has a lot of different components, then they need to come together. And I think I tried to express in this speech that the assembly part is important for us, and to make it so simple as simple as possible, but I think we have still a long way to go to make it simple enough. So I go through very briefly what the structure, the double-walled grid structure means. It means if we look at the node, then we split every edge to two sides, and connecting them up, we can achieve in a node a three-dimensional curvature, and through this one we can produce relatively complex shapes. The input is not limited to triangles, quads, or any regular geometry. Our input is line network, which can be turned into structural framework. And just to point out that there is this option, because all the project I show you is triangles, quads, and hexagonals, so just to give this one away. That was early prototype for the tab structure. And now I briefly stop on 3 projects, which all had a little bit different aspects what we learned. The first one on the left side is a SUTD Pavilion original project. In between there was a paper project for the exhibition, and the third one on the right is the tab structure. I don't think we have given a right name for that so far. So we were given a site, so what I do now is I go from the big picture to small and back again. So that's the site. Then we designed it was a cafe in the beginning, but it turned out that we can't put the water and so on. So it was just a shelter. There was a line network what we were tweaking around. And this line network was very important to give us flexibility, and also the communication with other parties who were doing calculations. It was easy to communicate with a very simple geometry. but just the lines don't describe vectors, so we had this metadata for the lines. And I used the Rhino, which has all these options to just embed extra information to. So that was our engineers trying to find out how the structure layout works. Then we got the engineering data. Based on that, we made the dimensions, cladding, and now I'm focusing on the cladding was important structural element because the forces throughout the axis had to travel as short as possible to for this kind of degree 6 networks. Usually you have this lot of bypasses. Then we had this site module, which was easy to assemble, and this small structural element, which was triangle, and fabrication element was reduction, this kind of very small, thin plywood element. Then what happens with this custom-built software is usually you write things for a different representations. You need to write things for 3D, you need to write something for 2D, and they kind of split up, and you hope in the end of the day they all come together. So what we had is we took this structural element, we just used the layout of the quad, we packed them, we added extra holes and also embedded numbering system, because if you just cut something once, you want to make sure that there is no mistakes and people are sourced from mistakes, so we just wrote all the numbers directly on the boards. These boards came out from CNC, and that's kind of a brief overview of all the data going through and coming together. So everything landed in one of the sites where we sorted things on the shelves. It was partly student involvement in the project to show them how tedious is to put together all the architectural sites. So next time they know when they design that somebody needs to work on that. Hinges were purely temporarily solution. They didn't carry any real force, but idea in the beginning was, oh, maybe we can do the hinges and then they can start carrying out the force. Later on, it turned out the hinges stayed, but they didn't work anymore. So the project usually evolves during the different conditions, and some things are redundant in one point, but they still somehow stay. Assembly process, sorting, another set of components in between, lot of different sorting, assembling, and it just goes on. And it took us like a month to put all this together. It was way too many components end of the day, because like it just piled up. First we thought like maybe we can get through like with one port, then it turned out we need 4, and then it just in this single node had 110 components. So we weren't very happy with the result in that front. So there's, just going through a couple of images. Now the site work, that was only construction document on site. So that was, since everything was embedded on a structure, you just need to guide them down like where this component should be. So having this very embedded system helped us on site, because like the person who couldn't speak any language I did, I could explain him in a couple of hand gestures how things work. And I think that was something important in this project too. Even though there was many components, it was still possible to describe how this thing should work. Just clicking through. We didn't allow students on site. It was a construction company. And next project was way simpler. It was paper structure. Again, we started with a 3D model. And the thing is, like, there's a the same model can provide the scale model with the different joints and the final model. So you actually work with one geometry with multiple different outputs. So in a previous project, we had a dedicated output for the engineers to collaborate. So this one has like this scale model, because for exhibition, you want to get all the graphics right and all the small details. And it is very easy we can do like one model every day and just glue things and see how the small changes affect. That's final layout for the reboard. That's a paper-based material. Cutting with a knife cutter. Okay, they were printed first, then cut, and then delivered as a flat sheets to the site. And on site, it was just bolting them together. It was very lightweight structure in that sense. And that just, you fold them up and everything worked. Just showing some pictures. Okay, the third one is today what you can see in exhibition. Just wanted to show what was happening behind. Again, we were mostly working on a line network. It was polylines, curves, and anything we can just tweak around. And that allowed us to use other softwares. You can just plug into the Kangaroo and do relaxation, and you can just do the fabrication through this module. There was like one guiding surface to just get sense what's going on. There's a 3D representation, how things should look like, if there is any like intersections, how the bolts fit. The thing is, like with the bolts, with the triangles, we face like if they get too close, the hands don't fit. With the hexagons, it's much better. They are much open. So that's the layout for the CNC. And also, like this project, since we used the CNC head, which has this thickness, we had to get rid of all the tiny corners to allow the CNC head to travel. That was that's the process for the CNC. Some layouts for the, and again, this kind of strange layout. That was only site drawing we used. A lot of help from the local volunteers. I didn't show them for a half day what it's gonna end up with, so they can just focus on assembly and they see like just putting things together. It is very parallel operations, right? Because you can work on a structure multiple different locations, and and the drawings are embedded. So it's just it's actually a little bit tedious, but it worked, and it was a very interesting process on that front. I have after these images, small clip to play. So maybe I ask somebody in the back to start the movie. That's not my movie. That's not my sound, but. Maybe I should comment, I don't know, it's awkward silence. Because we have discussion. Yeah, let it play. It was one of the most challenging parts to get another structure on top of the another ones. I just wanted to show that that everybody will see that it's not so simple, and we had great help from the tab side for organizing and assembling, and thank you very much for having me here.